Let's take a deeper look at some capacitors, shall we? Good day and welcome back to Mike's Radio Repair and Restoration. Today we're going to take an in-depth look at some of the capacitors that we run into in our tube radios. We're going to look at some of the properties. We're going to talk about how some of them fail. We're going to talk about the big concern about installing certain ones backwards. We're going to do a little testing. We're going to do a little checking. And hopefully at the end of the day, we'll all learn something about the capacitors that we deal with on a regular basis. So I'll go on with my usual whining here. If you are enjoying our series of videos here, maybe take a moment and subscribe. Get that front row seat. Get the notification when we put out a new video. I know I have tens of thousands of people who are watching these videos. Many of them return many times to look at different videos. Certainly wouldn't hurt you to click the subscribe button and get that early notification when we release new videos. So if you could do that and support our channel, that would be just fantastic. So today we're going to look at capacitors, and the first ones we're going to look at are the ones that don't cause us much trouble. So just let's get set up and get a closer look at the bench. Okay, so the first ones we're going to talk about are the ones we don't really need to talk about. But us electronic guys like to talk about things that don't necessarily need to be talked about, and we'll talk about them anyways, even though they don't need to be talked about, because it makes us happy. If it makes us happy to be happy, well, then we'll be happy. So these are the ones here that don't cause us a lot of grief. I put out an earlier video about identifying these, and let's just go through them. These are typical ceramic disc capacitors, and generally they don't cause trouble, and we don't replace them unless they have proven to be in failure. And there are different types of ceramic disc capacitors ranging all the way up to NP0s. They're often called NPOs in the trade, but they're actually NP0s, and they're quite a stable capacitor. But you may run into these guys, and we don't bother with them unless you suspect or there's something wrong in the circuit and you prove that one is in failure. I mean, they do fail, and it's usually because something else catastrophic happened in the circuit. I have seen that, but it's pretty rare that one will just up and fail, like a good old wax paper capacitor. These guys here are silver mica capacitors. They also are very prone to not failing. I think in the last couple of calendar years, I have had one go bad on me, and it was not necessarily totally bad. It just drifted quite a bit, which was very odd. Silver mica capacitors are used in RF circuit because they don't respond to RF heating. They stay fairly accurate. As long as they're enclosed and they're not leaking in any ways. Like some silver micas were used in RF transformers where the environment, humidity could get at them, and they began to decompose inside those RF transformers. But encased in these types of materials, they last quite a period of time. So we really don't need to talk about them. Just keep them in the back of your mind if you've got something going on in the circuit in a disc cap. There could be an issue, but probably not. Some of the Hammerland later receivers all came rather than using wax papers or other types of capacitors. They changed to these disc caps, and it really made a big step up in the receiver's reliability. So with that, we'll move on to the next type of capacitor. So next, let's talk about electrolytic polarized capacitors. And you see a bunch here on the bench. All of this whole lot here are all electrolytics. And they come in the various forms. You may see them in their older radios, from the upright cans that sit on the chassis to other ones like this one that would belong in, say, a Helicopter S38 that gets strapped under the chassis, and smaller ones also that get strapped under the chassis. Now, these are time-limited devices. They dry out, they fail. And let me give you an idea here if I can. I've taken one apart and put it in a plastic bag here. Now this is the paperish insulating material that separates the aluminum plates or that they use in the capacitor. It's impregnated with something. I don't really know what it is. Maybe somebody out there can tell me what they use to impregnate this paper with. But it's got a bit of a greasy feel to it. And when you take it out of its case and you leave it out in the environment for a day or so, as you can see here, it dries out very quickly and it becomes brittle and it'll crumple like a leaf. So these old can capacitors aren't necessarily sealed very well, and over a great period of time, that paper material will dry out. When it dries out at high voltage, it tends to fail. And this is the inside of a electrolytic capacitor that came out of a Helicopter S40. As you can see, it's actually burnt and probably caught fire inside the can, and the paper has gone dry. So they dry out. That's the bottom line, and they fail. They lose their ability to do their jobs. So these older guys, I don't generally bother testing. They're old, they've done their job, they've been in circuit for a while. During a restoration project, I just replace them. But if we wanted to test them, we can do so, and you can get a reasonably accurate and a reasonably affordable meter to test what's called the ESR, which is equivalent series resistance of a capacitor. And what that is it is a measurement of the loss of useful energy put into the capacitor that doesn't come back out. And they call it a loss, but it's not really a full loss. It winds up being dissipated as heat. So when a capacitor begins heating and heating up, you know its ESR is high. So I'm just going to change the angle of the camera to see if we can get focused on an ESR meter and check a couple of old ones and a few new ones and talk a little bit more about ESR. Just before I continue to do that, I'm going to put up a chart for newer capacitors that shows what given microfarad range at a given voltage and what the ESR should be brand new. Sometimes capacitors sit on a shelf for a very long period of time, and even just that without use can cause them to go bad, to dry out. But some that have sat on a shelf for 6 or 8 months, the ESR may be a little bit off, but will recover when the capacitor gets into use. So you're measuring your ESR, looking at your chart, and you'll be able to kind of sort of establish, like if your ESR is supposed to be 1.7 ohms and you're measuring 2, there's a good chance that that capacitor will reform and recover. But we'll look at all those details in just a little bit minute. Let's see if we can get that focused in on our meter here. Just 1 minute. I'm hoping you can read that. It's giving us a microfarad level right now, showing 0. But in smaller text, down here along the bottom, it has an ESR. So first we're going to check a new cap, and this one is 22 microfarads at 450 volts. Now before you connect this up to your ESR meter, you need to be certain it's fully discharged. If the capacitor's got any level of charge in it, and you connect it to the meter, the chances of damaging the meter are quite high. So I just connect a jumper wire across them to make sure like they're discharged like this. So now we know that our capacitor is safe to test, or it's not going to smoke up our meter. And we have our negative side that we have here now. and we have a positive side that we put here. And so it's showing about 21 microfarads, and it's ESR, and I just happen to know that's pretty good. It's showing 1.19 to 1.2 ohms. So that's a brand new cap in good shape. Everything is happy. Let's look at maybe one that's not so happy. Just let me get my jumper wire going here again, folks. This is a much older capacitor. I'm going to say from maybe the early 60s. So I'm just making sure it's fully discharged before testing it. Put my jumper wire away. Again, we make sure we get the polarity correct. Here, the negative is on the back side and the positive is here on the front. Okay, so that's showing this capacitor, before we continue, is 20 microfarads rated at 250 volts DC, and it's showing 19.2 or so, but the ESR is all the way up at 7.2 ohms. So you know that's a tired and dry capacitor that needs to be changed. That's pretty self-explanatory right there. Now let's look at this guy here, and again, just let me just do the short out here. This is a double capacitor. There's two inside of it. What have we got? We've got a 50 and a 30. These, I hate these cheap jumper wires. I don't know why I use them. I should just get rid of them. So we just want to just make sure these are shorted out here, and that capacitor is discharged, which it is. So we'll connect our negative on the back here. And let's connect to this side here first. And that the 50 is showing 57, which is odd, which is high, but its ESR is all the way down at 0.56 of an ohms. So that part of that capacitor is still not bad, but it being so high at 57 is maybe suspicious. Let's look at the other one now. And the other one, what was it rated for here? I got no memory. 30 microfarads. Okay, so it's not even registering, and it's showing an ESR all the way up at 25 ohms. So that one side of that capacitor is dead. But I think that underscores the dry out factor. And that's the important thing to understand, is these electrolytes dry out. They need to be replaced. And I think I've mentioned this before in my videos, that when you drag home an old radio, do not plug it in. Do not turn it on until all the capacitors have been changed. You can really do some damage to unobtainium, as I call it. You can break something or burn something in a radio that you might not be able to replace. So if it's old, original stock, or beyond 20 or 30 years old, without question, these guys, replace them. Put some new guys in. It's not hard. Sometimes you can buy from other vendors similar looking cans that fit. I often cut these open and restaff them. I put new modern capacitors in them, and I've got videos out there showing how I did that. Or in the case of an S38, you can mount them on a terminal block under the chassis. Sometimes you can leave the original one in place but disconnect it so the chassis looks original. So there's lots of different things you can do, but now, ESR is the king. You know, the higher the ESR, the more the loss, the more the heating, the more the problems. So you're really looking for that low ESR. And I'm hopefully going to throw up a chart here, and so you can see exactly what standard ESR specifications are all about. And maybe I'll post it to the community section on my YouTube page here, but I'll certainly will post it to our help group on Facebook. So if you'd like to join that, you're absolutely welcome to do so. I'm going to set up the next type of capacitor next, so I'll be right back. This is the interesting one. Okay, these are types of capacitors that we really are very common in our radios. We've got the old style and we've got some new styles here to look at. But what we want to do is we want to discuss the old style and their issues and how they're constructed. So let's take a look at this guy first. These old guys here. These are wax paper caps. They are, without question, known to fail. They fail routinely. They fail left, right, and center. They fail up and they fail down. They're bad, and we really need to change them. And these are very similar, older caps that have a similar construction. And these they call bumblebees. Now, one of the things, and I'm going to just go and put up a picture here in a second, is how these capacitors are constructed. They are, of course, two foil layers with a piece of paper in between them that are wrapped up. So there's an outer foil layer, and one of these leads is attached to that foil layer. And you can induce noise into that foil layer. So if this portion of the capacitor is attached to a high impedance, extremely sensitive input of a tube, and say a noisy B plus wire goes past this capacitor, or say some noisy AC filament lines go past this capacitor, they can induce noise into that outer shield, into this lead, and into the next tube of stage. And you really don't want to do that. You would rather turn it around and have it connected to the outer shield to the output tube rather than the high impedance input side of that circuit. We're going to look at a couple of pictures here in just a second, so let's do that now. Okay, here's an electrical equivalent of one of these old wax paper caps. And if you can imagine, again, it's two pieces of foil with a piece of paper embedded with wax rolled up, and this is kind of sort of electrically what it would look like. So you have one lead which is connected to an outer layer of foil, and the other leads are connected to an inner layer of foil. So the outer shield is unprotected from noise induction, and again, that's like filament supply noise, poorly filtered B plus, other high level signals, other static that could get in. And if this is connected to a sensitive input of the next stage of a tube, you may be inducing noise you don't necessarily want in that stage. But if you look at this side, the inner, it's better protected from noise induction. So that's a pretty straightforward thing to understand. Now let's just go and look at a schematic here where that might apply. Let's look at C2 here now. It's a 0.005 or 0.0047 would be the modern equivalent to that. So if you're going to connect the shielded end, you want to connect it to ground, and you want to protect the part of the signal path anyways, or you want to keep noise out of the power supply here, or out of this portion of the circuit. So you'd want to connect your shield to ground. And if you come over here and you look at C34, it's a 0.005, modern day 0.0047. We have the output of V5 feeding the input of V4. And the last thing you'd want to do is have the shield connected to this very sensitive input here, because you may be inducing noise. You'd rather have the shield connected to the output of V5. So, I mean, we're splitting hairs and we're getting technical, but if you've got a fancy radio, that's what you need to do, assuming your capacitors respond this way. And that's the big ticket that we're going to look at next. We're going to look at some of these old capacitors and how they respond with the shield problem. And we're going to look at some new modern ones and how they respond as well. So we'll do that next. Okay, I have an oscilloscope set up as a makeshift visual voltmeter. And I'm only connected to the Y input, which is vertical, and I have the sweep off. So the only thing we're going to see is vertical deflection on the oscilloscope. And of course, the more vertical deflection, the higher the voltage. So let me just see here now. We can give you a little demonstration here. Right now, the input is grounded. So we're seeing a nice, fairly sharp, clean dot in the center of the screen. When we unground it, it begins to pick up noise. As soon as you touch it, you can see what's going on there. So now let's prove or disprove our shield theory here. Now I've got a bumblebee capacitor, and this is a good one for demonstrating this type of thing. So we'll connect it up one way. Don't know which way it is here now, but we'll just touch it. And we don't see the dot is deflecting very much at all. Maybe just a little bit, but nothing. So let's turn it around. Here we've turned it around. Now I'm touching it. Now you can see there's significant deflection. So we know that this lead of the capacitor is that outer shield. So all of the older caps had this affliction, which isn't necessarily a bad thing, but it's a good thing to be aware of. And certainly that shield is something you want to connect to the lower impedance port of the circuit or ground or whatever. Now, people have been extending this ideology to newer capacitors, which I have two right here. These are the newer modern film capacitors. So let's check them, shall we, and see if they have a similar response. You would think they would. You know, it's a logical conclusion to think that they would have a similar response. So we'll connect it up this way, and we'll touch. We have a little bit of a response. Nothing serious, nothing to write home about. Let's turn it around this way, 180 degrees. Do the same check. And the response is identical. With that particular cap, there was not a difference between side to side. And that is interesting for me. Let's go on with another modern day film cap. These are very common that folks use to restore their old radios routinely. And these are the ones people are worried about installing backwards. So here we're installed one way. And again, we have a similar response as to the yellow film cap. Let's turn it around 180 degrees. Flip her on. And it has exactly the same response. So these don't respond in the same way that the old ones do, and you don't have to worry about installing these backwards. So I think that's the takeaway. I might add that I believe that the small amount of deflection we're seeing with these modern caps is more the fact that I'm just getting close to the end terminals of the wire than I am coupling noise from my body into the capacitor. It's my understanding that these new capacitors are most likely have a shield to protect against this. It's probably an extra layer of conductor material that's not connected to either of the pins that gives it probably a little bit of shielding and keeps the noise down. So I don't, again, I don't think that installing these one way or the other has any significant benefit. Learning the components that you use and learning their properties is important. These are the capacitors that I use that don't respond to this outer shield problem. Maybe you have a different brand by a different company, and it certainly doesn't hurt to set up and check. So I think that's the takeaway, is to know what you're dealing with. Do your testing. Like anytime I put a resistor or a capacitor into a circuit, the first thing I do is test it. I've had capacitors that were incorrectly marked on more than one occasion. I've had resistors that were well out of their range. I've had new electrolytic capacitors where the ESR was terrible. So I just have the basic equipment here in this small little part of the lab to do the basic checks on things before you install them. So again, you know, knowing your components, they're different from different manufacturers, and everybody's human and makes mistakes. So every component I put into a radio, I check. Is it okay? Is the ESR okay? Is it within the manufacturer specs? I have a nice LCR meter that you can get cheap on Amazon. I've got a cheap ESR meter. Again, you can get it cheap on Amazon. And that was one of the focuses of setting up this small bench. I have a much bigger lab, but using equipment that was relatively easy to find and affordable. And on the bench here, I have an older oscilloscope here that I bought for $35. It works okay. It's not the greatest thing, but for the home hobbyist guy, it's certainly the cat's meow. So anyways, that's kind of an in-depth look at capacitors, and it should raise enough question marks and exclamation points with you that you want to check things before you install them. Understanding everything is important. So I hope you found that somewhat informative. Again, if you have questions, leave them below, or you can join our Facebook help group. But we certainly thank you for tuning in today, and if you could maybe make an effort and hit that subscribe button and maybe a like button, I'd really appreciate it. So until the next one, we'll see you again.